And so begins the next chapter in our calculus journey. Literally. Here's the first video on the subject of double integrals. Now, as I've done frequently, what I'd like to do is first do a quick review of a concept from Calc 1, which is the definite integral. So the definite integral does the following. Suppose that we have an interval along the x-axis from a to b. Suppose we have a nice generic looking function, y equals f of x. And we're interested in finding the area that is contained below the curve, that is in between x equals a and x equals b. So that area was defined as the definite integral from a to b of f of x dx. Now, before we had access to the fundamental theorem of calculus, there were a number of things that we did to generate what we refer to as a Riemann sum. So first thing we did is break that interval from a to b into some number of subintervals. So we break it up into a bunch of little tiny intervals like this. And the most generic way that we do it is we say that we're breaking it up into n subintervals. And the length of each of those subintervals was equal to delta x. And it was the length of the entire interval divided into n equal parts. So we referred to the starting point as x0. Then we had x1, x2, x3, so forth and so on, until we got to x sub n. Then, depending on whether we were doing a left-hand approximation, right-hand approximation, midpoint approximation, whatever it was, we said select a representative point from each subinterval. That point needed two things. First off, it needed an index. We refer to this as x sub I. We use the star to let us know that we really are talking about any point within each of those subintervals. So you could pick the midpoint, you could pick the left-hand endpoint, you could pick the right endpoint, you could pick the point that's 70% of the way through the interval. Honestly, the way that you selected the point didn't really matter. What did matter is that you plug this x value into the function. And the reason that you did that thing is because you're now getting a y value associated with the x value. So on any given interval, what you have just done is gotten yourself a y value to be associated with that x value. I refer to this as the approximating area. We used a rectangle for this because the rectangle has a very simple area formula, which is base times height or length times width, whatever you want to call it. So we'll say a sub I for each of these, and that was f of x sub I star, that's the height, times the length of the base, delta x. Now that was for any one of these intervals. We need to do this for all of the intervals. So we're going to sum the individual areas. And the way that we did so, we used summation notation. We said we'll take the sum from I equals 1 to n. Of course, now that we've been through Calc 2 and we have access to series, summation notation tends to be a little bit more straightforward to understand. Finally, this only approximates the total area. So this will be approximately equal to the total area. The way that we turn it into the exact value of the entire area is we allow the number of subintervals to go to infinity. That is, we're going to allow delta x to become infinitesimal. So then we say let n go to infinity, and we get that the area is exactly equal to the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I star times delta x, which in turn became a definite integral. Now, if you had me for Calc 2, you probably heard this over and over again, but anytime a statement starts with the limit as n goes to infinity of the summation from I equals 1 to n of something, that bad boy is about to turn into an integral. Didn't matter if it was arc length, or work, or surface area, whatever. It's about to turn into an integral. Now, with those things in mind, let's talk about how that relates to what we're going to do today. So first thing is we are going to define a rectangular region. We'll use capital R to represent a rectangular region. This is going to be the set of all ordered pairs xy such that x lies in between A and B and y lies between C and D. This is a rectangular region. So if x goes from A to B and y goes from C to D, then the region in question says x has to be between A and B and y has to be between C and D. You'll notice that those values are included, which is why I'm using a solid line rather than a dashed line. Now imagine that we have a function z equals f of xy. Now this technically would be a surface that is above this region. Our goal is going to be to find the volume below z equals f of xy within our rectangular region. Now essentially what we're going to do is the exact same thing as what we did for the definite integral. We are just going to be doing it for the x-axis as well as for the y-axis. So first thing we did is said let's break the intervals into a certain number of subintervals. So we'll say break the interval from A to B into, we'll use m subintervals of length delta x, which is b minus a divided by m. Now we'll say and break the interval from C to D into n subintervals of length delta y, and that'll be equal to d minus c over n. Now for me this is going to be a super easy process because I used to work at pizza places and we used to cut up rectangular pizzas all the time, but if you need a little bit of practice, I understand. Of course, now that I've said that, we'll see how well it actually goes in practice. Oh yeah. Yep, little shaky. You can tell it's been a while since I've used a pizza cutter. Now you'll notice that that breaks the rectangular region into a bunch of little, well, sub-rectangles. So we'll point out this breaks R into a total of, well, in our example this was m equals 6 and n equals 4 over here, because you see 1, 2, 3, 4, 5, 6 subintervals and 1, 2, 3, 4 subintervals. You'll notice that there are a total of 24 subrectangles now. That's not a coincidence that that is the product of m times n. This breaks R into m times n subrectangles of area, and we'll call it delta A. Now delta A would simply be delta x times delta y, or if you prefer, delta y times delta x, since multiplication is a commutative operation. Later on we'll describe the significance of reversing that order. Next we'll select a representative point from each subrectangle. Now for this, we're going to need a couple things for this as well. It'll still take on the form x star and y star, but because we have two different variables now, we need two different indices. most typically the two indices that you'll see used, indices is the plural of index, you'll see sub ij. So those are supposed to be two different numbers. Now, this essentially just means take any point from within each of these subrectangles. Could be one of the corners, could be the midpoint. Really, it's just any point from within each of those regions. Now, once we take this point and plug it into the given function, that will turn into a z-value. A z-value is going to be the height of a, well, technical term for it is rectangular prism. More common term, box. So plug this into f. So we'll get f of x sub ij star comma y sub ij star. And this is now the height of a box that we are creating. So for definite integrals, we were creating rectangles to add up. Here, we're creating rectangular prisms or boxes to add up. So the volume for each of those, we'll call it v sub ij, is equal to f of x sub ij star, y sub ij star, times the area of the base. Generally speaking, the way that you calculate the volume of a three-dimensional object, if it's got that nice cross-section, nice consistent cross-section, is you take the area of the base and you multiply by whatever the height is. Then we get to add them up. Now, because we have two indices, that also means that we are going to need a total of two summations. This is what's referred to as a double summation. Now, I is what we're using for x, and for x we broke that into m subintervals. So we'll say I goes from 1 to m, j is the second one, so j will go from 1 to n is what we used for the c to d. And we'll take each of these individual volumes and we will add them all up. Then, to get the best possible approximation, we'll say let m and n both go to infinity. This is going to give us, and I'm pretty sure I have room for it, so I'm really proud of myself here. So the total volume is going to be equal to the limit as m and n approach infinity of the double summation. I goes from 1 to m, j goes from 1 to n, of f of x sub ij star, y sub ij star, times delta a. This is equal to, now on the flip side I mentioned that anytime you see something that starts with the limit as something goes to infinity of the summation of something, that's about to turn into an integral. This one, because it's a double summation, is going to become a double integral over the rectangle R of f of xy dA. This is the definition of a double integral over a rectangular, oh boy, region. Oh yeah, that totally fit. Double integral over a rectangular region. Now, the question becomes, does that mean that we need to set up a Riemann sum every time we want to do one of these? The answer is, boy, that would really suck, wouldn't it? However, there is no fundamental theorem of calculus as it applies to double integrals, so the question becomes, what do we actually do? I'll describe that in our next video.